Hi, greetings. In this class, we will discuss about plane electromagnetic waves in lossy dielectric. In the previous class, we have discussed about plane electromagnetic waves in lossless dielectric or free space and free space. In this class, we will discuss about plane electromagnetic waves in lossy dielectric. So, in practical situations, when we see dielectric material do possess certain amount of conductivity, we can't say that dielectric materials don't have conductivity, but they possess certain amount of conductivity. So, by Maxwell's equations from Ampere's circuital law may be written as del cross H equal to J plus dou D by dou T, where J is the conduction current density and D is the displacement current density. So, as you know, J is equal to sigma into E, where sigma is the conductivity of the material and E is applied electric field. And D is the displacement current density, which is given by epsilon into E, where epsilon is the permittivity of the medium. So, accordingly, we can write as del cross H equal to sigma E plus epsilon into dou E by dou T. Representing in phasor form, dou by dou T can be written as J omega. So, accordingly, we can write it as del cross H equal to sigma plus J omega epsilon into E. And another Maxwell's equations from Faraday's law, we can write as del cross E equal to minus dou B by dou T, where B is the flux density. And it is related to magnetic field intensity by the relation B equal to mu H, where mu is the permeability of the medium. So, we can write as del cross E equal to minus mu into dou H by dou T. And again, representing in phasor form, we can write dou by dou T as J omega. So, del cross E equal to minus J omega into mu H. So, and as you know, the propagation constant gamma is given by alpha plus J beta, where alpha represents the attenuation constant and beta represents the phase constant. And it is given by root of J omega mu into sigma plus J omega epsilon. So, multiplying this with J omega mu, we can write it as root of J omega mu plus J omega the whole square into mu epsilon. So, from the first term, you multiply numerator and denominator with J omega. So, J omega the whole square by J omega mu sigma plus J omega the whole square mu epsilon. So, root of J omega the whole square can be taken J omega as outside. So, here also J omega the whole square, here also J omega the whole square. So, take J omega outside. So, J omega into root of mu epsilon. So, this term root mu epsilon minus here we have taken the term is mu sigma by omega. So, we have written like this. So, gamma equal to J omega into take root mu omega epsilon outside. So, here 1 minus, so when you take mu epsilon outside, so in the denominator you will be having simply J sigma by omega epsilon. So, the terms sigma by omega epsilon may be designated as loss tangent. So, the term sigma by J omega epsilon is called the loss tangent, which is again, so we can represent gamma equal to J omega root of mu epsilon, take root mu omega epsilon outside into root of 1 minus J sigma by omega epsilon, which is equal to alpha plus J beta. So, by applying the binomial theorem, that is by applying the binomial theorem to the second radical, that is 1 minus J sigma by omega epsilon the whole power half. Applying binomial theorem, the binomial theorem can be written as 1 plus x the whole power n equal to 1 plus nx plus n into n minus 1 by 2 factorial into x square plus goes on. So, now here you consider this term as x, that is J sigma by omega epsilon as x, and the whole power half as n. So, n equal to half and x equal to minus J sigma by omega epsilon. So, when you write it as 1 plus n into x, so 1 plus 1 minus half into J sigma by omega epsilon. So, this first two terms alone you take, neglect the remaining term. Neglecting the higher order terms, we can write as J omega root epsilon into 1 minus sigma J by 2 omega epsilon. So, when you multiply J omega root mu epsilon plus omega, so here minus J square, J into minus J square, which is minus of minus plus. So, plus omega root mu epsilon sigma by 2 omega epsilon. Neglect this higher order term. So, again you have J omega root mu epsilon plus sigma by 2 root mu by epsilon. So, neglect the higher order terms. So, take the first term alone. So, you have sigma by 2 root mu by epsilon plus J omega root of mu epsilon. So, you have this term, neglect the higher order terms. So, now you can rewrite gamma as alpha plus J beta and take out the real parts and the imaginary parts. So, comparing the real parts and imaginary part, so this is the real part which is given by alpha, sigma by 2 root mu by epsilon. This term is beta, which is phase constant. So, the phase constant is given by omega root mu epsilon. So, alpha equal to sigma by 2 root mu by epsilon and beta equal to omega root mu epsilon. So now the intrinsic impedance equation can be written as root of j omega mu by sigma plus j omega epsilon. So now you take j omega epsilon outside in the denominator. So it is 1 plus sigma by j omega epsilon. Again, you know, sigma by j omega epsilon is called the last tangent. So you bring this to the numerator, the whole power minus 1, and again apply binomial theorem to this. So when you apply binomial theorem to this, you can rewrite it as mu by epsilon 1 plus j sigma by 2 omega epsilon. So 1 plus x by 2. So x by 2. So this term is x. So x by 2 we can write it as j sigma by 2 omega epsilon. So this is the expression for intrinsic impedance. And another Maxwell's equation is del cross h equal to j plus dou d by dou t. So j we have written as sigma e, and d dou d by dou t we have written as j omega epsilon e. So the first term is called the conduction current density, and the second term is called the displacement current density. So del cross h equal to jc plus jd. Jc represents the conduction current density and jd represents the displacement current density. So the ratio of conduction current density to displacement current density is given by jc by jd equal to sigma e by j omega epsilon e. Okay. So sigma, so this e and e will be getting answer. So you will be having sigma by j omega epsilon. So when you take the magnitude part alone, so relieving this j, we have sigma by omega epsilon. So this is called the last tangent. And when you plot it as so this represents the jc, j sigma e, and this represents the jd, j omega epsilon e. The angle between the conduction current and the displacement current is 90 degree. So and the equivalent current density is j equal to sigma plus j omega epsilon into e. So addition of the conduction current and the displacement current, and this is called the last tangent. This ratio is called the last tangent and is a measure of impurity of the given dielectric material or medium. So it measures how pure the dielectric material is. See, for a dielectric material, the omega epsilon value is very much greater than sigma, and for conducting medium, so the sigma is very much greater than omega epsilon. Okay. So when you substitute for good conductor, so this is the expression for intrinsic impedance. As I said, for a good conductor, the conductivity is very much greater than the j omega epsilon, which represents the dielectric current. So conduction current is very much greater. So you neglect this j omega, so you neglect this j omega epsilon. So you simply have root of j omega mu by sigma, or we can write it as, so take j outside, root j, for j the angle is 90 degree, for root j the angle is 90 by 2. So the angle becomes 45 degree, and the magnitude becomes root of omega mu by sigma. And the angle of 45 degree can be written as cos 45 plus j sin 45. Cos 45 is 1 by root 2 and sin 45 is again 1 by root 2. So 1 by root 2 plus j by root 2. So this omega can be written as 2 pi f. So this here you have 1 root 2 and the denominator we have 1 root 2. These two will be cancelled. So ultimately the intrinsic impedance value is root of pi f mu by sigma into 1 plus j1. Topic for the next class. Next class we will discuss about plane waves in conducting medium. And questions, I would like to ask the questions. Define last tangent of the dielectric. So it is sigma by omega epsilon. And for the dielectric, omega epsilon is very much greater than sigma. And for conducting material, sigma is very much greater than omega epsilon. So derive expressions for attenuation constant, phase constant, and intrinsic impedance for plane waves and lossy dielectric. So this is the thing which we derived in our class. What is the criterion for expression for last tangent for dielectric? So as you know, for dielectric, omega epsilon is very much greater than sigma. Hope you understand the concept. Thank you.